Hello everyone. In previous lectures, we have studied complex frequency domain analysis for continuous time signals. In this lecture, we will study complex frequency domain analysis for continuous time systems. First, we will discuss S-domain description for continuous time LTI systems. As we know, for a continuous time LTI system, we can use this differential equation to describe it. By the differentiation property of bilateral Laplace transform, we can obtain S-domain equation to describe the LTI system. It's the equation in S-domain. According to this equation, we can get the system transfer function h of s. H of s is defined is ys over xs. The system transfer function h of s is an important function to describe the system in S-domain. We can find the hs is only related to the system properties, has nothing to do with the input signal and the output signal. H of s can describe causal systems and non-causal systems. The relationship between the h of s and h of t, according to the definition of h of s, we can find the relationship between the ht and the hs. They are Laplace transform pair. For a causal system, its impulse response h of t is causal signal. In this case, the unilateral and bilateral Laplace transform of causal ht is identical. So, for a causal LTI system, hs can be obtained by unilateral Laplace transform of input signal and output signal. This is a definition by the unilateral Laplace transform. If the system is causal, we can use unilateral Laplace transform to find its h of s. Here are some methods to determine h of s. The first one is by impulse response. We can use this equation to get the h of s. And we can use the input signal and the output signal. According to the definition, we can get the h of s. And we can use the differential equation to get the h of s. For example, determine h of s for the ideal integrator and the differentiator. The relationship of input and output for the integrator is in this equation. According to this equation, we can get the impulse response for the system. The h of t is a unit signal. So we can get the transfer function for this system is 1 over s. For the differentiator, the relationship of input signal and the output signal is in this equation. The impulse response h of t is this signal. So we can get the transfer function for this differentiator is S. We can use another way to get the transfer function. Here is another example. We can use this circuit to find its transfer function. The circuit is a causal LTI system, so we can use unilateral Laplace transform to determine the transfer function. First, we can get the S-domain circuit. In last lecture, we have studied the model in S-domain for the capacitor. So use the model in time domain, we can get this model in S-domain. According to this model in S-domain of the circuit, we can get this equation. And according to this, the transfer function h of s, we can get the impulse response h of t. Here is another example. The differential equation for a causal LTI system is as this equation. Determine its hs and ht. As the system is causal system, so we can apply the unilateral Laplace transform to this equation. We can get the transfer function for the system. According to the definition, you can get the h of s in this equation. This number, real number, is the largest real part of poles. In this expression, there are two poles. One is -1, another is -2. The largest real part of the poles is -1. By inversion of unilateral Laplace transform, we can get the ht in this expression. In this lecture, we have studied the S-domain description for LTI system. That's all for today. See you later.